Okay, we'll begin. I'm not turning on video because of the internet problem, but hopefully the internet will last for the class. So are there questions? Okay, so if there are no questions, let me begin. Okay, so first I want to make a correction in the formula that I gave for a number of diagrams in a number of terms in a diagram without bubbles. Okay, in fact, the formula that I gave I think is valid for m equal to 1, but at higher order you have corrections, and I'll explain this today. Okay. So let's consider 5 to the 4th theory. Okay, that the theory that you have been considering. Okay. And let's suppose that we have an amplitude. Okay, I have a Green's function with 2n external phi's, okay, and m internal vertex. Okay, m internal points, which means that each of these points have 4 phi's coming out. Okay, and we'll denote by s 2n m the number of terms in. Okay, this is not connected diagram, in a diagram without bubble. Okay, just correct this. This is in a connected diagram I'll introduce later today. Okay, so S 2nm is the number of terms in a diagram without bubble, okay, which has these 2n external points and m internal points. Okay, and this is what you want to count. Okay, the reason that you want to count is because the sum of the combinatoric factors of all the Feynman diagrams should add up to this. Right, this will be a check for any calculation that one does. Okay. So let's start by writing down the total number of terms including bubbles. Okay, that there is no confusion about. Okay. So here there are number of phi's is 2n plus 4m. Okay. So that's what you are calling 2k earlier. Okay. So total number of terms including bubbles is 2n plus 4m factorial divided by 2 to the power n plus 2m and n plus 2m factorial. Okay. Now we have independently another counting. Okay, that if we have a bubble with k internal points, okay, then there are 4k phi's coming out of these k internal points, because each internal point has 4 phi's coming out. Okay. So then the corresponding formula, we can use the same formula. Okay. The number of terms in bubble with k internal points is given by this formula over here. Okay. 4k factorial divided by 2 to the 2k times 2k factorial. Okay, so what I was calling a k earlier now has become 2k. Is this clear so far, these two form expressions? Okay, so with this I'll now write down the formula for S 2nm. Okay, and in fact this will be given as a recursive formula. Okay, that if we know S 2n for lower order result, then you get S for the mth order result. So let's try to understand this formula. So this is the number of terms that we'll get in diagrams without bubbles with 2n external lines and m internal line. 2n external points and m internal points. So this is the total number of terms. And we are supposed to subtract from this total number of terms the number of terms that involve bubbles. And here I have written down what you have to subtract. Okay, so I'll try to explain what these factors are. Okay. So you have to subtract all terms with bubbles. Right? Now the bubbles may have either one internal point. Okay, of course there are no bubbles with 0 internal point. Okay, we need at least some phi's to be able to form a bubble. So there can be a bubble with 1 internal point or 2 internal points, 3 internal points, and so on. Of course there are no external points for a bubble. So if there are k internal points in the bubble, we know that there are these many diagrams. So this tells you that how many diagrams are there, how many terms are there, not diagrams, how many terms will there be in a bubble with k internal points. This, you multiply this by the number of terms that will be there in diagrams with 2n external points and m minus k internal points. Okay, why m minus k internal points? Because the total number of internal points we know is m. Okay, that's what you are counting. So this is the number of terms that you will get with 2n external points and m minus k internal points. Okay, yesterday I had replaced this by a similar formula. But this formula, of course, counts diagrams without bubbles as well as diagrams with bubbles. Okay, that's why you shouldn't use the same similar formula here. We just write it as S2n m minus k. And now there is a final factor, which also I didn't write down yesterday. This tells us in how many ways you can choose this k internal points. See, altogether you have m internal points. But this tells you how many ways you can choose the k internal points out of the m internal points. Okay, because those will give different terms. Okay, although you will count them as same Feynman diagram, those will actually give different terms. And this factor, if you remember, you had encountered earlier when you are trying to show that the total expression actually factorizes into the product of sum over terms without bubbles and 1 plus sum over bubbles. Okay, so that's this combinatoric, this factor m choose k. You can also write it as the m choose m minus k. Okay, how many ways you can choose these m minus k internal points out of m. Okay, it's the same result. And then, of course, you have to sum over k from 1 to m, because that can be bubble with 1 internal point or 2 internal point, 3 internal point, all the way up to m internal points. Okay, so this is the formula, and what it tells us is that if you know S for lower order diagrams, right? Lower order means what? Lower order means less number of powers of lambda, right? Because m is the number of internal points, so that's the power of lambda that we'll get. Okay? So this tells you how to represent the number of terms at without bubbles, okay, at a given order, okay, lambda to the m, in terms of the number of terms in the same Green's function, but at a lower order power of lambda. Okay, lambda to the m minus k, where m minus k is necessarily less than m, because k here runs from 1 to m. So this is a formula then you can use, okay, to count how many diagrams, how many terms are there in diagrams without bubbles. So this is what I have written here. The last kth term, okay, it gives the number of terms in bubble diagrams with k internal points times the number of terms in diagrams without bubble with m minus k internal points and 2n external points. And then finally, the number of ways k internal points may be chosen out of m internal points. Are there questions on this? So you should go through this carefully to check if I have missed any other factor. Okay. And also you can try to work it out in the context of explicit examples. Okay. Just take some examples and count this S2NM. You can of course count it explicitly and see if that number agrees with what you have here.
So,
yes, go ahead, please.
Sir, you are saying that in a total diagram, there is a m internal point, and we are choosing k point in m.
Yes.
Oh, okay. Okay, sir. Okay.
Yeah, because k points are in a part of the bubble, right?
Okay. Sir, yes, sir. Sir, sir, M is a K contain only bubble only. On M is contained bubble and also without bubbles.
Exactly.
You are saying.
Exactly.
Okay.
So total number of terms including bubbles. So M contains everything, right? M is the total number of internal points.
Okay, sir.
Of which part may be part of the bubble and part may be part of the other diagrams without bubble, right? That's here. So this is the giving you that how many terms are there in bubble diagrams with k internal points. This is giving you how many terms are there in the diagram without bubble with m minus k internal point. And this is telling you in how many ways you can choose those k internal points out of it. Right? M is the total number of internal points, which is being distributed into the bubble and the diagrams without bubbles.
Okay, sir. Thank you.
Any other question? Okay, so the other point which I have already sent you an email, okay, the Ion asked about the symmetry factor of a Feynman diagram. And the point is, I think in general, okay, symmetry factor is referred to as whatever comes in the geometry at the end. Okay. So in 5 to the 4th theory, for example, if you have a diagram with m internal points, then you have a 1 over m factorial, right? That comes from expanding the exponential of hi to mth part. That gives you 1 over m factorial. Then you have 1 over 4 factorial to the m because of the lambda over 4 factorial term. And then you have combinatoric factor. So the symmetry factor is normally referred to as the inverse of this. Okay, and I think what the numbers that Ayano is mentioning agree with whatever you get from here. Okay, so that's just a definition of what I mean by symmetry factor of a Feynman diagram. Are there questions on this? Okay, so let me proceed.
So,
yes, go ahead, please.
On what we did yesterday regarding considering instead of time going to some tau 1 minus iota epsilon, we considered energy or like in the same spirit, the mass going to m square minus iota epsilon.
Yes, okay.
And we looked at the in appropriate limits, the final result will come out to be the same, the Green's function.
That's right, yes.
In this theory, maybe all of these are consistent with each other, and maybe we can do something more uh, in this specific theory with 5 to the 4 perturbation. But in general, in let's say in something like normal harmonic oscillator, considered as a 1 plus 0 dimensional theory,
yes,
field theory. In that, we don't have this mass term, and any additional perturbation we add, we either have to directly say that the Hamiltonian goes to some h times 1 minus iota epsilon and carry forward the calculations. Or in my point is that depending upon the theory, the prescription needs to be changed.
Yeah, okay. The point is, even the harmonic oscillator in particular does have the analog of a mass term, right? The half k q square.
Yeah.
That k is like m square.
Yeah, yeah. So in effect, it's like saying the Hamiltonian itself is changing.
Well, you replace k square by k square minus I epsilon.
Yeah.
Right? So of course, yes, Hamiltonian is changing, and then you have to take the epsilon goes to 0 limit.
Yeah. My point is that how do we ensure that, like in general, k might not be the only parameter that we have. Like in Klein-Gordon, we only have one parameter, the mass. But in general, when we start adding perturbations or other theories, we can have more than one parameter. So can we ensure that our mechanism is consistent?
Okay, so the point is that if you consider, okay, so in any at least in quantum field theories, okay, that you when you do perturbation theory, okay, and this is in the context of perturbation theory that we are discussing, right? Because we are trying to understand how to evaluate Feynman diagrams. So in perturbation theory, the unperturbed Hamiltonian, right, the analog of the H naught, okay, is always quadratic, okay? And it has some kinetic term and a mass term. Okay, in some cases the mass term may be 0, okay? In which case you just replace it by m square and then write m square minus I epsilon and then set m equal to 0. Right? So that you can do. And then the higher order terms, right? As you said, here there is lambda 5 to the 4. In general, there will be many such interaction terms. Okay? But as long as you are keeping them as interaction, okay, we know that they are not going to affect the leading order term, right? As long as you have made sure that the leading order term is damped, then the interactions are not going to affect this, at least in perturbation theory. So what you do in perturbation theory is that you take the leading order term, which is the quadratic term in the fields, right? In this case, there is a single field phi. In general, there will be multiple fields, each with its own mass square. You replace each of these mass squares by m square minus I epsilon, and then carry out this procedure.
Yeah,
if you consider abstract quantum field theory, which doesn't have this structure, then of course you have to do something else. But in perturbation theory, you always have a quadratic piece, right? And that's the part you try to regulate.
So we also have to sort of ensure that even the diagrams that have diverging factors, like diverging contribution to the sum,
Yes.
even those are similar sort of divergences in the two different prescriptions. Like in
certainly. Yeah.
Sorry.
And in general, they will not be. Okay. In general, they may not be. But at the end, if the theory is renormalizable, what one can say is once you extract the finite expression, okay, which I'll discuss later today, how to extract at least the principle how to extract finite expression, then you can show that the different regularization will give the same result.
Okay.
But of course, when you are regulating, right, then there is no guarantee that they will give the same result.
Yeah.
So we'll discuss how to deal with divergences today.
All right.
Are there other questions? Okay, so let me remind you the momentum space Feynman rules, and then we'll work out some examples. So what was our goal? Our goal was to calculate the Fourier transform of this Green's function as a function of x1 to xn. And this was the Fourier transform. And what we did was that we started with the Feynman rules for this, okay, which we had studied earlier, and we translated this into Feynman rules for computing G tilde. So the rule was the following, that we draw Feynman diagram with external points carrying momentum P1 to Pn, and we have chosen the convention that these momenta flow outwards. Each propagator also carries momentum now, okay, in fact, two momentum on the two ends. And now the rules that we used is that the momentum is conserved at the vortices, so which means that the sum of the momenta entering a vortex vanishes. Okay, that's so you will simplify the momentum leveling using this rule. And the second rule is that the momentum is conserved along the propagators, which means that the sum of the oppositely directed momenta at the two ends of a propagator vanishes. Okay, so if the propagator carries momentum p at one end, it should carry momentum minus p at the other end. And then we said that we use this to label the momentum flowing in a diagram as you do in labeling the currents in an electrical circuit. Okay, instead of saying that if you have electrical circuit with say resistance, okay, instead of saying that you assign arbitrary current at the on each link, okay, on each resistance, okay, and then apply the the current conservation at every junction, okay, we normally use the current conservation already while labeling the currents. Okay, so the same thing we will do to label the momenta that flows in a diagram. And then the final rule is that at the end, okay, if at some vortex or propagator momentum is not manifestly conserved, then we include the delta function for that vortex or that propagator explicitly in the final expression. Okay, so this is what you have to keep in mind, and I'll discuss several examples of this. And the other rule is that if some momentum is not fixed in terms of external momenta, then of course you have to explicitly integrate over it. Okay, and I will see examples of both of these today. But this is the general rule. So what I'll do is that I'll illustrate this by some examples, and then I'll come back to these rules and see if there's any confusion. So here is a simple Feynman diagram. This in fact we discussed yesterday, okay, but let me go through it again. So you have a 4-point function, 4 external points, okay, P1, P2, P3, P4. Okay. And this is the diagram we are considering, okay, one internal point, which is here. So we label the momenta in such a way that the momentum conservation is manifest in all the propagators and vortices. At least that we try to make it manifest as far as possible. So here you see momentum conservation is manifest along this propagator. This is P1, this is minus P1. Okay, this is P1 because the external momentum is P1. Okay, so it has to flow outwards P1. Similarly, here we have already conserved momentum on this propagator because this is labeled as P2, this is minus P2. Similarly, here this is as P3, this is minus P3. This is P4, this is minus P4. Okay. So on all the propagators, momentum conservation is manifest. But now you see that at this vortex, momentum conservation is not manifest because the total momentum that is entering the vortex adds up to minus P1, minus P2, minus P3, minus P4. So because this is not manifest, you have to explicitly add the momentum conserving delta function that is associated with this vortex. So this is what we have said, that we have leftover delta function, which is here. Okay. 2 pi to the 4 delta 4 minus p1 minus p2 minus p3 minus p4. Okay. And there is no unfixed momentum in this diagram. All the momenta have been explicitly fixed. Okay. So the net result for this diagram, okay, let me write it there, the full result. So first of all, of course, the vortex will have a minus I lambda over 4 factorial. That is here. Then you have the product of the propagators, okay, except the delta functions. So this propagator, for example, had I over minus p1 square minus m square plus I epsilon. The second one will have I over minus p2 square minus m square plus I epsilon. So these are these 4 propagators. Okay. So let me maybe remind you where they come from. Okay, I think the expression for the propagator were written down earlier here. Okay. You see that this is the expression for the propagator of this. The delta functions we have already used up in doing the integral, okay, over the q1, q2, etc. This is still left, right? And this delta f tilde q1 is exactly this factor that I'm writing. It's this factor. And then because we have one vortex where momentum conservation is not explicit, okay, we have to put in explicitly the momentum conserving delta function. And finally, you have the combinatoric factor for this diagram. And that comes because the 1 can connect to this vortex in 4 ways, then 2 can connect in 3 ways, 3 can connect in 2 ways, and then the 4 has no choice, it connects to the remaining. So that's 4 times 3 times 2. So this is the complete expression for the momentums for this diagram, for this contribution to the momentum space Green's function to this object. Are there any questions on this? Is this procedure clear?
Sir?
Yes.
When we have found the final expression, shouldn't we put epsilon equal to 0?
Yes. Of course, here we should put epsilon equal to 0. Okay. But normally we keep this epsilon, right? Because you may want to do something more with this, right?
Oh, okay.
Okay. But yes, eventually, of course, you have to set epsilon equal to 0. Any other question? Okay. So I'll now describe a second diagram, which is here. Okay. So let me just point out one thing. So from now on, right, this diagram is a little cluttered, right? I mean, there's p1 minus p1, etc. Okay. So from now on, what I'll do is that I'll not write down these things explicitly. It will be understood that if you are, for example, in a propagator, okay, it will be understood that if we have not written down two momenta on two sides, okay, it's automatically conserved. Okay, that it will be understood that the other one is minus p1. Okay, if I have not written the momentum level explicitly. Okay. So with this, we will try to simplify the drawing of this diagram. So in that notation, I'll drop this minus p1, minus p2, minus p3, minus p4, and only write this p1, p2, p3. Okay, because here the conservation is explicit, manifest. So I have drawn the second diagram with this notation. Okay. So here I have drawn this p1 in the propagator. That means this is minus p1. Okay, automatically is conserved. This is p3, so this is minus p3. Okay, p2, so minus p2, and p4, so minus p4. Now let's try to see what happens to the momentum conservation here. So total momentum here has to add up to 0, right? Total entering momentum should be 0. So it's minus p1 minus p3, okay, entering from here. Now, how much will go out? Now we know the total momentum that is going to go out of this must be equal to p2 plus p4, okay, because at this vortex also there is momentum conservation. Okay. So in anticipation, even though we have not applied the momentum conservation explicitly here, in anticipation you already know that if P1 plus P3 comes in, okay, it will be P2 plus P4 total momentum going out. Okay. But the momentum of this line, okay, it cannot be determined. Okay, there is nothing that can determine how much momentum will go out of this. Okay. So you just call this L. Once you have called this L, okay, this momentum that is going out of this is fixed because you see minus P1 and minus P3 comes in. L has gone out, so minus L. Okay, so the total momentum that is going out from here must be minus P1 minus P3 minus L. Okay. And with this, you can check that the total momentum here is conserved. Is that clear? Is there any confusion here? Okay. So total momentum, so if we label it by L, yes, go ahead, please.
Sir, please repeat again this thing. Sir,
Okay.
minus P2 and minus P4 is also incoming.
Yeah, so
Minus
that's
P2 and minus P4.
right. See, either from this vertex or from this vertex, okay, the idea is that the momentum conservation here, okay, will give the total momentum that is flowing out of these two lines, right? Momentum conservation here cannot determine the individual momentum. Is that point clear? Let me
Yes, sir.
let's focus on this vertex. Okay, we know minus P1 and minus P3 are coming out. Okay. So what will it determine? It will determine the total momentum that is flowing out of these two vertices. That's clear?
Yes, sir. Yes.
Similarly, here you see P2 and P4 are going out. So this will determine the total momentum that is flowing in these two lines. Okay, how much momentum is entering. Okay. So whether you work here, okay, or work here, okay, you can only determine the total momentum, okay, the sum of these two. Okay. But you cannot determine them individually. Okay. Which means that this momentum remains undetermined. This momentum L. Okay. Once you fix this to be L, this must be minus P1 minus P3 minus L. Or you could have applied the momentum conservation here first, right? There, then if you fix this to be L, then this would have been P2 plus P4 minus L. But either way, you cannot fix it.
Okay, sir. Okay.
Is that clear?
Sir, yes, sir.
So we have decided to apply the momentum conservation here. So that tells you that if this is L, then this is minus P1 minus P3 minus L. And now we see that at this vertex, the momentum conservation is not manifest. Why is it not manifest? Because it's L, and here it's coming minus P1 minus P3 minus L. So total is minus P1 minus P3 that is entering here. Okay. On this line, what is entering here is minus P2. On this line, what is entering is minus P4. So you have a delta function of minus P1 minus P3 minus P2 minus P4. Okay. So that's what I have written here. Okay, delta function, of course, the minus sign you can change to plus sign inside the argument of the delta function. But you will get an explicit factor of 2 pi to the 4 delta 4 P1 plus P2 plus P3 plus P4. That's coming in this way of labeling. That's coming from this vertex. But if you are labeled the other way, okay, where you make it manifest here, then it will come from this vertex. Okay, it doesn't matter how you label it. Okay, but the fact remains that at one vertex, the momentum conservation will not be manifest, and that will give a term like this. But now, because this momentum is not fixed, okay, you have to integrate over it. Okay, and you integrate by d4 L over 2 pi to the 4. Right? Because all integrals had d4 L over 2 pi to the 4, and all delta functions had 2 pi to the 4 delta 4. Right? That's why this particular structure. Okay. So for any unfixed loop moment, any unfixed momentum, you have a factor of d4 L over 2 pi to the 4. For any vertex where or propagated where the momentum conservation is not explicit, you have to put in this delta function, and then that's it. Right? That's you integrate. Okay, what do you integrate? You integrate what you would normally count as a contribution to Feynman diagram, right? So let's see 1 over 2 factorial. That's because it's of order lambda square. Right? There are two internal points. Okay. Then minus I lambda over 4 factorial square. Right? That's coming because each of these internal points gives a minus I lambda over 4 factorial. These factors are the product of propagator factors for P1, P2, P3, P4. These I can take out of the integral because these do not depend on L. Then you have the propagator for here and here, right? That's delta F tilde L and delta F tilde minus P3 minus P1 minus P3 minus L. That's here. Right? If you had used this vortex, you would have gotten P2 plus P4 minus L. But that's of course the same because of the delta function. And then finally you have the combinatoric factor, right, which you had calculated earlier. Right? It starts with 8 and then 4 and then 3 times 2. Okay, so that's what you have to put in here. Okay, and here I have written explicitly the expression for what we mean by delta F tilde L. Is this clear? This expression? So this gives you a specific contribution, okay, order lambda square contribution to the same amplitude G tilde P1, P2, P3, P4. Right? You have 4 external points, but this is a second order contribution, right? And this is of course not the only second order contribution. There are other Feynman diagrams which contribute, but this is one of them. Okay. So this L that is being integrated over is typically called the loop momentum. Okay. And it's called the loop momentum because you can easily convince yourself that for every independent loop in the diagram, we have such a 4 momentum that needs to be integrated over. Okay. And again, you can draw analogy with the circuits, right? Any circuit that has no loops, right, there the current flowing through each resistance, okay, can be determined just from current conservation at the vortices. Okay. If the circuit has a loop, okay, then there's an undetermined current that is flowing along the loop, okay, which then you have to determine by making sure that the voltage drop along the loop goes to 0. Right? That's an extra word. Okay. So just like while labeling currents, right? How many undetermined currents are there? Okay, before you apply the voltage drop rule, okay, is the number of loops. Similarly, here the number of undetermined momenta will be the number of loops. Okay. Another way of saying this is that if you have a loop in a diagram, right, then you can easily convince yourself that you can satisfy momentum conservation, okay, simply by adding a current that is adding a momentum that is flowing along the loop, right? Because if it flows along the loop, then every vortex, whatever enters, comes out. Okay, so that's the one way to see that for every loop you'll get an unfixed momentum. Okay, there's no way momentum conservation can fix a momentum that is flowing along a loop. Is this point clear? Any questions? Now here I should also add the reason that we are working with momentum space Green's functions, okay, is because we will see later in these lectures that the momentum space Green's functions are what are directly related to the observable quantities in particle physics. Yeah, of course, I mean, it doesn't mean that the position space Green's functions are not useful. Okay, in many condensed matter applications, the position space Green's functions are the useful ones. But in standard application to particle physics, it's mostly the momentum space Green's functions that are directly used. Okay, and that's why we want to learn how to calculate momentum space Green's functions directly by summing over Feynman diagrams. Are there questions? Okay, so later in today's lecture, if I have time, we'll work out more examples. Okay, but let me now proceed. Okay, I think you have got some idea of how to evaluate momentum space Green's functions. But the best is that you draw Feynman diagrams and you practice drawing it, evaluating it. Okay, in momentum space, that's the only way to really understand the subject well. So now let me come to the divergences. Okay. So in the momentum space representation, all divergences essentially come from integration over the loop momentum. So for example, in this expression that we had here, this delta F tilde L goes as 1 over L square there's a minus L square minus M square plus I epsilon. And then this one has 1 over minus P1 minus P3 minus L whole square minus M square plus I epsilon. Okay, so this is what I have written here. And now if you see its behavior at large L, right? Let's see if this integral is converges at large L. So at large L, the denominator factors, right? This is like L square. And here, of course, L is much larger than P1 and P3. These are fixed momenta. So it goes as L square whole square. Right? L square times L square. So roughly, if you think of D4L as L cube DL, okay, by going to appropriate polar coordinates, okay, you get L cube DL over L to the 4. Okay, that's like DLL inverse. Okay. So basically what this is saying is that this integral is logarithmically divergent, right? Because upper limit is infinite. Okay, so this integral is logarithmically divergent. So these divergences that we see here are called ultraviolet divergences. Okay, divergences which come from large loop momentum. And these are the ones which can be removed by renormalization. Okay, but it can be removed only in a special class of theories which are called renormalizable theories. Okay. And as I have emphasized that in these lectures we will not try to distinguish between these renormalizable versus non-renormalizable theories, because that will become clear only in the next course, okay, where you understand renormalizability in more detail. But it's the ultraviolet divergences that you deal with using this procedure for renormalization. And now you would have seen that the earlier the divergence that we encountered, right, delta f xx, I said that whenever two arguments coincide, then we get divergence, right? And this divergence is in fact of the ultraviolet type. And we can see this explicitly. This is the expression for delta f xy. And you see that if you set x equal to y, then this becomes integral d4L I over minus L square minus M square plus I epsilon. The oscillatory part goes away. Okay, so the I epsilon doesn't really help here very much. And at large L, this is quadratically divergent. So again, because these divergences are associated with the large L, okay, this is ultraviolet divergence. Okay. And because of this, we have not tried to remove this earlier, okay? Because as I said, all ultraviolet divergences can be removed at one go using the idea of renormalization, okay, which I'll discuss briefly later in today's lecture, okay? But only briefly. Okay, I'll just give the general idea of how we get rid of the divergences. But is this clear? Is the origin of divergence clear? Any question on this?
Sir?
Yes, go ahead, please.
Only two vertices. Instead of 1, 2, 3, 4, we just had 1, 2.
Yes.
Two internal vertex diagram. So we'll have three connections sort of a diagram, like one connecting to X, two connecting to Y, and X and Y connecting over three edges.
Yes.
That will also give a divergent diagram, right?
Yes, it will. So
Although
let's
it's
draw
not.
this diagram maybe to make things clear. I think you're talking about this, right?
Yeah.
Yes.
Although when we study the large momentum behavior, we'll have some D4L upon L6. So yeah.
There'll be two loop momentum now. Okay, so in fact, this is one of the examples we will discuss.
Oh.
I'll do it right now. Okay, so let's suppose that this is P1, this is P2. Okay, so at this vertex, right? See what is fixed? Sum of the three momentum is fixed, right? Okay, because there's a minus P1 going here. Okay, so you have to label it as L1, L2, and this will be, this is this way I say. So this one will be minus P1 minus L1 minus L2, right? Okay, so this will have integral d4 L1 over 2 pi to the 4 d4L2 over 2 pi to the 4. Okay. And then you have 1 over L1 square minus L1 square minus M square plus I epsilon 1 over minus L2. Oops. And then you have 1 over the third one, right? Minus P1 minus L2, L1 minus L2 square. So this has two integrals, right? And three denominators. Is this visible? Or the bottom part?
Yeah.
Okay, so it has two integrals, right? d4L1, d4L2. So it goes as L2. So that means it's d8L basically, right? Over L to the 6.
Yeah.
And that's why it's divergent.
Yeah. So what order of divergence do we say here? Like logarithmically
It
or
will be
what?
quadratic. This has quadratic divergence.
Yeah.
Right? Because there are 8 parts of L,
Yeah.
8 L integrals, right? And 6 parts of L in the denominator.
Yeah.
So this is a quadratically divergent integral. That way, this is the same as the other one, the delta XX that we got. Okay,
Yes.
let me draw that diagram. Okay, let me. So I'm erasing this. Is there any question on this? This is clear to everybody that this is 8 parts of L in the numerator. There are 8 L integrals, right? So it's like d8L over L to the 6, right? 2 from here, 2 from here, and then 2 from the last one. Okay, so I'll erase this and then draw the.
So,
Yes, go ahead, please.
by the diagram, sir, we can find like which type of the divergence in the diagram, or like yeah, we have to calculate integral
Well,
and
yeah,
find.
typically in a renormalizable theory, you can figure out by the diagram, number of external lines essentially tell you whether the diagram is divergent or not. Right? In 5 to the 4th theory, for example, diagrams with number of external lines 2 or 4 are divergent. The diagrams with external lines that is more than 4, right? So 6 may be divergent, but those divergences can all be reinterpreted as divergence in a 4-point function or a 2-point function. Okay, there will be sub diagrams which will diverge. So in general, you can figure out, okay, what are the divergent diagrams, what would be the divergent diagrams just from the number of external lines.
Okay, sir.
Okay, so let me draw this one. This diagram, for example, right? This is also quadrilateral divergent, right? This is the delta f xx kind. Okay? But in this language, in the Feynman diagram language, you will draw it like this. So this is P1, that's P2. And if you call this L, right, you see the L goes out from here, L comes back, right? The same L. So here you will get a delta 4 P1 plus P2. I'm not writing the 2 pi to the 4 factors. Okay, because P1 coming in, right? So let me write, there's a plus L minus L, okay, that just goes away. Okay. But then you have integral d4L over L square. L minus L square minus M square plus I epsilon. So this is also quadrilateral divergent, right? Okay. Now, as I said, if you have diagrams with more than 4 lines, right, it's typically not divergent, but it can have sub divergences. So let me explain what that means. So let's say we draw a 4.6 point function. So okay, so this is a contribution to a 6-point range function, right? Okay. Now this is divergent. This, let's say P3 going out. So this momentum here will have to be minus P1 minus P2 minus P3, and then you have this is going this way, and then P4, P5, P6. Okay, so this is divergent, right? This is divergent because you have integral d4L over, this gives you minus L square minus M square plus I epsilon, and then 1 over minus P1 plus P2 plus L square minus M square plus I epsilon. Okay, so this is logarithmically divergent, as you can see, right? Because d4L over L to the 4. Okay. But this logarithmic divergence can be assigned to a divergence in a 4-point function in the subdiagram. Okay. So once you have understood how to make sense of this, okay, then the 6-point function is automatically made finite. Okay, so that's the sense in which I said that whether the diagram is divergent or not is in some sense controlled by the number of external lines. Is this clear?
Yes, sir.
Any other question on this? Okay, so let me go back. Okay, so these are ultraviolet divergences. Now I should also add that there are also divergences from vanishing denominators, right? Sometimes the denominator may vanish, okay, like for example when L square plus M square is 0, because L square, if you remember, is not positive necessarily, right? L square is what? Minus L naught square plus L vector square, right? So L square plus M square can be 0, right? So whenever that kind of divergence appears, right, and these divergences are in fact most severe when M is 0, okay, then you get infrared divergences. Okay. And but whenever you have infrared divergences, one can show that they always have physical origin. Okay. So if you ever run into infrared divergences, okay, that basically indicates that the kind of questions you are asking or you are trying to what you are trying to compute is something that is not physically observable. Okay. So this is the reason why ultraviolet and infrared divergences play quite different role in understanding of physics. Okay. The ultraviolet divergences are genuinely there; they have to be removed by renormalization, okay, if possible. Okay. Infrared divergences, on the other hand, are there only when you have asked the wrong question. Okay. So if you ever find infrared divergence in your calculation, you will know that you have asked some wrong question. Okay, again, I will not say very much more about this in this course. Okay, but just 2 things to keep in mind. Are there questions? Okay, so now I am going to give a 1-page summary of what exactly one means by renormalization. Okay. Although just by looking at the summary, you will probably not really get the grasp of what is going on, right? But as I said, if you take the second course in quantum field theory, you will learn this in more detail. Okay. So, as I have said, all ultraviolet divergences actually come from integration over loop momenta from the region where the loop momenta are large. So, this way one goes about dealing with ultraviolet divergences is the following. So, the first step is to somehow make them finite. Okay, you cannot deal with infinities, right? Because infinities, I mean, if you subtract two infinities, you don't know whether it's finite or infinite or whether it's zero, right? You have no idea. So you have to the first step in dealing with ultraviolet divergence is to make it finite, okay? And that procedure is called regularization, okay? That you have to find the regularization that makes the integral finite. Okay? This can take various forms. Okay? Often the final result doesn't depend on how you regularize, okay? Although the intermediate steps can become simple or complicated depending on how good your regularization is. So for example, we could just put a large cutoff lambda on the loop momentum, right? We said that we only integrate over loop momentum, which is less than lambda. Or you can be more sophisticated and you can say we just multiply the integrand by some damping factor like e to the minus L mu square over lambda square. Okay. So divergences of the kind that you have seen are all polar divergences, right? So once you have exponential damping like this, then they all become finite. Okay. And you can see that if lambda is large, then for finite loop momentum, this factor is just 1, right? So it doesn't do anything. But once the loop momentum starts becoming larger than lambda, then it dampens the integral. Okay, so it makes the integral finite. So this is just a little more sophisticated version of this, but there are more sophisticated versions of how you regularize ultraviolet divergences. Okay. Now, of course, if you do this, the result will depend on how you cut it off. Right? It will depend on lambda. And we also know that it will eventually diverge as you finally take the limit lambda goes to infinity. Okay. We of course eventually want to take lambda goes to infinity limit, right? Because it's not a physical cutoff. So then you put the cutoff in place, okay, and then you compute physical quantities. Okay, let's call them say A1, A2 up to N. In fact, there are infinite number of physical quantities that you can calculate. Okay. And those typically involve either the masses of particles or scattering amplitudes and scattering probabilities and various other things. So you compute these quantities A1 to N as functions of the parameters of the theory, right? So in the 5-4 theory, for example, the parameters are M and lambda, right? And of course, everything depends also on the cutoffs, capital lambda. Okay, so physical quantities are computed as functions of M, lambda, and capital lambda. Okay. So let me call this as some function Fi of M, small lambda, and capital lambda. Okay, and let's suppose that we have chosen some N physical quantities. Okay, as I said, that can be in general, there are infinite number of such physical quantities, but let's just assume that we are interested in finite number of them. So I equal to 1 to N. So we calculate these functions Fi in perturbation theory as an expansion in powers of lambda. And these you can in principle calculate, okay, from Feynman diagrams once you have put a particular rule for cutoff. Okay. But of course, you know that these functions that you have will all diverge as lambda goes to infinity, right? So you are not going to take lambda goes to infinity limit at this stage. So the third step, okay, so is it clear so far? Are there questions? So everything is fine, I can proceed. Okay. So the third step is to pick any two of these physical quantities. Okay, why two? Because you have two parameters, M and lambda. So pick any two of the physical quantities, let's call them A1 and A2. And then solve these first two equations. So you have A1 as some known function of M, small lambda, and capital lambda. A2 is some known function of small m, capital, small lambda, and capital lambda. Okay. So you solve for M and lambda in terms of A1, A2, and of course capital lambda, right? Because capital lambda also enters the description of these functions. Okay. So you invert these functions, F1 and F2. And that will give M as a function of A1, A2, and lambda. Let's call this function G1. And that will also give this small lambda as a function of A1, A2, and lambda. Let's call this function G2. Is this clear? Okay. So now what to do is that we want to now express A3, A4, the other physical quantities, okay, A3, A4 up to N, not in terms of M and lambda anymore, okay, but in terms of A1 and A2. And the way you do it is that in the argument, okay, wherever you had M, okay, you replace it by G1 of A1, A2 lambda, okay, which you have found by inverting these relations. Similarly, whenever you had lambda, okay, you replace it by G2 of A1, A2 lambda, okay, and lambda. So this tells us how to express the physical quantities A3 to N in terms of two other physical quantities A1, A2. And in general, everything depends on capital lambda, which is a cutoff. And at this stage, we take the capital lambda goes to infinity limit. And what we find is that if the theory is renormalizable, then this limit is finite. See, Fi is an infinite function, right? If you keep this G1 and G2 fixed and try to take lambda goes to infinity, you get infinity. G1, G2 are also in general infinite functions, right? These are not inverted because F1 and F2 are have infinities. Okay, so you expect G1 and G2 to also have infinities. But the idea in a renormalizable theory is that once you express AI as a function of A1, A2 and lambda by using these, and now take the lambda goes to infinity limit, then the infinities that come because you are taking lambda goes to infinity of here, and the infinities that come because of the G1 and G2, those two exactly cancel, and eventually we get a finite function, which I can call Hi of A1. And this finite function, these relations are completely independent of the cutoff. Okay, how you had chosen to cut off the ultraviolet divergence. Okay, even though at this stage, in the intermediate stages, everything depends on the cutoff. So this then can be taken as a prediction of the theory, because this actually relates observable quantities to observable quantities, right? And as I said, because there are an infinite number of physical observables, you have infinite number of predictions from a given theory that you relate all observables in terms of, you express all observables in the theory in terms of two observables, A1 and A2. So this is the way one extracts physical predictions of a theory like 5 to the 4 theory, which has ultraviolet divergences, as you saw. Are there questions?
Sir?
Yes, go ahead, please.
So what exactly changes when we do things in this way? Because divergence is removed, you were saying.
See, what exactly changes is that when you do things this way, right, then this function is divergent, typically, okay, because G1 has been obtained by inverting F1. You take F1 and F2, which are divergent functions, so G1 and G2 are divergent functions. But now when you take the lambda goes to infinity limit, right, there are two kinds of divergences. One, because here if you keep M and lambda fixed and take capital lambda to infinity, that is divergence, right? Okay. But now because you are keeping A1 and A2 fixed and taking lambda to infinity, M and lambda themselves are also divergent. And these divergences cancel each other. Right? So it's a question of how you take the limit. If you keep M and lambda fixed and take capital lambda to infinity, then you have the usual perturbation theory, which is divergent. Okay? But if you also allow M and lambda to be divergent at the same time in an appropriate way, okay, so that A1 and A2 remain finite, then that same way of taking M and lambda to infinity to make A1 and A2 finite makes all the other AIs also finite. Okay? That's another way of saying this.
So can't this be, regularized using those analytic continuation method we used earlier?
No, that's not, because this is ultraviolet divergence, right? So it cannot be regulated. Okay, regulation is one thing. Okay? But at the end, you have to make sure that in the lambda goes to 0 limit, lambda goes to infinity limit, you get back finite answer. And that will not happen here. if you insist on keeping this small m and small lambda fixed and take capital lambda to infinity, you will not get a finite answer. Okay, so even if you regularize, right, you will not get back a finite answer in this limit. And this is unlike the regularization that we did earlier, right, with the epsilon, I epsilon. There, as the epsilon goes to 0, if you take the epsilon goes to 0 limit at the end, you get a finite answer, right?
Yeah.
That is not the case here, right? If the theory has logarithmic divergence, right, then in the limit lambda goes to infinity, you will get logarithmic divergent.
Yeah. Okay.
Okay, so that's the difference between what we did earlier, that epsilon goes to 0 limit and this lambda goes to infinity limit. So here what you have to do, so effectively what you are doing is that you are taking lambda goes to infinity, okay, but at the same time you are also taking small m and small lambda to infinity at the in a certain way, so as to cancel these divergences. Now, what is the surprising thing is that, see, what is not surprising is that you can do it for two quantities, right? If you take A1 and A2, okay, then there are two quantities and you have two independent variables to play with, right? M and lambda. And you can say we'll make M and lambda divergent as lambda goes to infinity in such a way so as to exactly cancel out the divergences. What is surprising, and that is the special thing about renormalizable theory, is that by adjusting these two parameters, M and lambda, okay, to go to infinity in an appropriate way, you can make all observables finite, right? Infinite number of observables, right, you can make finite just by taking small m and small lambda to infinity in an appropriate way. Okay? And how you take them to infinity is encoded here, right? Once you invert these functions, then this already tells you what you should do, right? Because you want to keep A1 and A2 finite and take lambda goes to infinity, right? That tells you exactly how m should go to infinity in that limit. Is this point clear?
So how do we sort of determine the domain of A1, A2 and?
Well, you determine the domain by seeing if the theory is sensible, right? I mean, if you find that there is some domain of A1, A2, right, where say you have particle with negative mass square, then you know that the theory is not sensible.
I mean, like, could you give an example for some physical quantity in, let's say, the Klein-Gordon theory?
Well, A1 could be the mass of the particle, mass of 5, for example.
Yeah, so we sort of, in the end, when we computed this, some AI in terms of A1, A2 and this capital lambda, and
Yes.
then take the lambda going to infinity limit,
Yes.
that A1 will run from 0 to infinity, like not run in the sense of integration, but keep as a number that lies with 0 to infinity.
Yeah, see, it can take any value from 0 to infinity, right? Unless the theory becomes sick in some other way, right? Suppose you try to take so you take A1 and A2, right? Let them run over any value from 0 to infinity, right? But you may find that some other observable, right, is taking unphysical values. Okay, as you try to run them from 0 to infinity, then you know that the theory has limitations, right? That it cannot, A1 and A2 are restricted. But otherwise, you just think of A1 and A2 as independent parameters, okay, and let them run all the way to infinity.
Suppose if we are taking mass as a parameter, we can maybe also take charge.
Yes, you can.
So should we run it over the Coulomb, like 1.6 into 10 to the minus 19 multiples, or?
Well, see, charge, okay, what you're thinking of is quantized charge, right?
Yeah.
Yeah, that's so, but the actual strength of coupling. So once you fix the unit of charge, then all particles have charge that is multiple of that unit. Okay, that's one thing. But what that unit of charge is, right, that's a parameter of the theory.
At this stage, yeah.
Yeah, so that parameter can be varied. That in a quantum field theory, right, the charge of an electron is a parameter.
All right.
That you can vary continuously. What you cannot vary is that once you have fixed the charge of the electron, right, then the charge of the positron you cannot vary independently. Right? That will be minus. I mean, that will not be an independent parameter anyway, right?
Yeah.
but one charge will be independent, right? And so the number of parameters that you have, right, that is determined by the number of parameters that you had in the original Lagrangian. Okay, like in this case, you have m and lambda, right? In the electrodynamics Lagrangian, you will see that there is a the mass parameters are there, and then also a coupling constant, right, which is what you are calling the charge of the electron. Okay? That's an independent parameter that you can vary.
Okay.
That will play the role of lambda, okay, in electrodynamics.
Oh, could you give some more examples of physical quantities?
Well, most physical quantities that people look at and or measure experimentally are the scattering amplitudes, right? Then you take two particles, collide them, and ask what is the probability of producing a certain final state, right? You collide two electron positron, say, right, head-on collision, and you ask what is the probability that you produce two electrons and two positrons at certain angles, going at certain angles in the final state. So those are physical quantities. And because you can vary the angle continuously, right? Or you can ask for any number of electrons and positrons. That's why the number of observable quantities is infinite.
Yeah.
But you can also consider more sophisticated observables, right? Like the positronium spectrum. That's also observable. What are the energy eigenvalues of a positronium? Any other question?
Sir?
Yes.
So here the final result for AI in the number 4 point, that depends upon A1 and A2. If we use some A3 and A4, then will the value change or remain the same?
Yeah, the functional form of course will change. Right? So quantum field theory, a renormalizable quantum field theory, what it does is that it expresses all the observables in terms of a finite number of observables. Okay? Now that finite number you can choose to be either mass and charge or something else, right? You can take, for example, the result of scattering as your independent parameter, right? So take scattering at one angle and scattering at the second angle. And then you express everything else, including mass and charge, as a function of that those probabilities. Okay? So that's also a perfectly good way to look at the theory, even though it's not very efficient perhaps. Okay? But what you choose as your as the basic observables, right, in terms of which you express everything else, that's completely up to you. And the functional form will change. Right? If instead of A1 and A2,
What I'm saying that the functional form might change, but will the final value remain the same, or that will also change?
Well, final value you measure, right?
Yeah.
That will remain the same.
How can we see that from here?
In a given theory, right? These parameters are fixed. Right? So A1 and A2 is fixed. Right? So all the other AIs are also fixed in a given theory. Well, maybe not in a given theory. In a given theory, these are parameters, right? But in nature, these are fixed, right? Nature tells you some particular values of these parameters. Like, for example, the charge of the electron, right? Charge of the electron is a free parameter in the quantum electrodynamics, okay, that we'll study. But nature gives you a particular value of that parameter. And similarly for all other observables.
Okay.
Is that clear, or maybe I didn't understand your question correctly?
I mean, sir, I was trying to say is that here this A1 and A2 in this theory come as just two, I mean, parameters to, I mean, renormalize these things, regularize these things. Now we can take some A3, A4 instead of A1, A2.
Yes.
And
So
then
A1 and A2 will be expressed in terms of a function of A3, A4.
Yeah.
Yes.
And then, I mean, how can it be said that the final value of AI is going to remain the same, because there are infinities here? These are not very regular things.
No, they are not infinities. That's the point. Now, if you take the lambda goes to infinity limit, these are finite functions. Right? The infinities cancel.
Okay.
Right? Yeah, if there are infinities, then of course you cannot do anything, right? But these, see, you look at this. Here there's no lambda, right? I have already taken lambda goes to infinity limit.
Yeah.
So here everything is finite. Okay, HIs are finite functions. There's an ambiguity. And now, if you want to express everything in terms of A3 and A4, right? What will you do? You will write A3 as H3 of A1, A2, and A4 as H4 of A1, A2, right? H3 and H4 are finite functions, so you can just re-express A1 and A2 in terms of A3 and A4. And then you use that to write everything else in terms of as functions of A3 and A4 instead of A1 and A2. Is that
Okay,
clear?
fine.
Okay, maybe I can write it here. Just 1 minute. So what I said is that we have AI equal to HI of A1, A2, right? Okay. So these are all finite functions. Okay, HIs have no divergences because I have taken the lambda goes to infinity limit. These are completely well defined. Okay. So if we want to express everything in terms of A3 and A4, right? What you will do is that you will solve A3 equal to H3 of A1, A2 and A4 as H4 of A1, A2. So these equations will solve to get A1 as, let me call this H1 tilde of A3, A4 and A2 as H2 tilde of A3, A4. Okay, these are just by solving these equations. Okay, two equations in two variables. So you invert them to write A1 and A2 in terms of A3 and A4. Is this clear so far?
Yeah.
Okay, so now what you can do is, suppose you want to now write A5. So A5, you will now write. Okay. So this was to begin with H5 of A1, A2, right? Okay. But you will now write this as H5 of H1 tilde A3, A4 and H2 tilde of A3, A4. Okay. So these are all finite functions. Sorry, not A3, A4. Yeah, A3, A4. That's fine. So this expresses then A5 as a function of A3 and A4, right? Okay. So you have expressed A1 as a function of A3, A4, A2 as a function of A3, A4, and A5, A6, everything now can be expressed as a function of A3, A4 just by inverting the relations. But the actual values, right, that is given by the nature, that of course doesn't change, right? That tells you specific values of all the quantities, A1 up to A infinity. Okay. And quantum field theory, what it does is that it gives relations between those quantities that you can check, right? You want to check if a given quantum field theory is the correct description of nature, right? So the way you check it is that you work out what the relations that quantum field theory gives, right? And there are various ways to express those relations. You can write everything as a function of A1, A2 or everything as a function of A3, A4. Right? And then you check if the actual observed values in nature obey those relations. Right? See, nature doesn't allow you to vary those parameters, right? Nature tells you the specific values of those parameters. Nevertheless, the reason that you can test this is because there are infinite number of predictions, and you can check those infinite number of predictions in terms of two quantities that you have to fix, right? For example, if you take the mass and charge as the independent variable, you cannot check within quantum field theory whether mass and charge comes out correctly. Okay, that's what you measure. But once you have measured mass and charge, right, then any other measurement, okay, whatever answer it gives, there is a prediction from quantum field theory, okay, which you can then ask, does it agree with what you observed in experiments? Is this point clear?
Yeah, it's fine.
Any other question?
Sir, in cases where this does not happen, do we reject the theory, or do we sort of say that our math is incorrect?
Well, typically we reject the theory, right? Because at least the standard rules of quantum field theory doesn't work. But then you can see if you can do something else, right? I mean, in string theory, for example, this doesn't happen, right? But in string theory, what happens is that there is actually a physical cutoff, right? All the integrals actually become finite, right? There's an analog of the lambda, which, oops, let me, I have to first, just 1 minute, let me stop sharing. Okay. So in string theory, for example, this cutoff is a physical cutoff. Okay, there is actually a lambda. Yeah. So this lambda is physical. Okay, it's determined by something close to Planck mass, and that's how you make things finite. But in quantum field theory, if it doesn't happen, right, then within quantum field theory, you cannot deal with this problem. Because in a sense, you would say you reject the theory. Unless you can find a way to put a cutoff and give some physical reason for why the cutoff should be there.
Sir, if we were to strictly believe that space was indeed a lattice with some lattice spacing,
Yes.
then also we'll have this cutoff, right?
Yeah, certainly. Okay, but then it has various consequences, right? If you have a lattice, for example, then the Lorentz invariance is not an exact symmetry. And then you have to worry about how to get Lorentz invariance, right?
All the continuous space-time symmetries will have to be reformed.
Exactly. Yeah, Lorentz invariance translation, nothing will be asymmetric. So lattice, people of course use lattice gauge theories. I mean, lattice quantum field theories are used very much, right? But that's again as a regulator, right? Eventually, you want to take the lattice spacing to 0, okay? But you can use lattice as a regulator. Okay, the role of lambda can be played by a lattice. Any other question?
Lastly, do we have any conventional theories that we use classically that are, when written as a QFT, are not do not follow this procedure?
Classical field theory. Well, I mean, it depends on what you mean by conventional theory. Electrodynamics is renormalizable. Right?
Yeah.
Gravity is not renormalizable. Gravity is a classical field theory. Okay, but it's not renormalizable. So indeed, that's an example. Any other question? Okay, in fact, that's the reason why, I mean, gravity, to quantize gravity, string theory is the best path so far. Okay, it's not a normalizable theory. Is this okay? Any other question? Arshit, you have a question? I can see Harshit, but I don't know if he's connected. Okay, let me proceed anyway. I think this is the last, almost near the end of the lecture. Okay, so in the rest of the course, we will basically avoid this problem by working with what we call tree diagrams. Okay, these are diagrams without loops. Okay, and typically the lowest order contribution to an amplitude comes from tree diagrams, right? That's why you basically work only at the lowest order. Okay, so you don't worry about loops and renormalization. But this will form part of the quantum field theory 2 course. Okay, understanding how to renormalize. Okay, and how to carry out this procedure that I described here in more explicit details. Okay, so this is the final thing that I wanted to mention. Okay, and that's the distinction between connected versus disconnected diagram. Okay, so now at the level of the diagram, it's very easy to explain. A connected diagram is where every point is connected to another point via a collection of propagators and vortices. Okay, like in A. Take any point on this diagram, you can go continuously to any other point. These are not connected. Okay, I mean, you can forget about C because that's not to be included anyway. Right? This is bubble. Okay, but this, for example, is not a connected diagram because if you start from anywhere on this line, you cannot go continuously to this part. So this is at the level of the diagrams, but actually at the level of the expression also there is a difference between connected diagrams and disconnected diagrams. Okay, and that's what I'm going to try to explain now. Okay. And so the point is that in a given Feynman diagram, okay, we have seen that every vortex and propagator has momentum conservation. Okay, whatever flows in has to come out. Okay, so here, if a momentum is going this way, right, the same momentum will be going this way, right? There's a momentum conservation on the propagator. Okay. At the vortex, if whatever momentum flows in from one side must come out from the other side. Okay, which is equivalent to saying the total momentum flowing in is zero. So because of this, okay, it's clear that the total momentum of all the particles must add up to zero. Okay, if you think of all of them as ingoing, right? Because momentum is not violated, right? If you pump in P1, suppose you take out P1 from here, okay, P1, P2, P3, P4. Okay. Unless you have violation at some point, right? The total momentum that is flowing out must be zero. Okay, and that we have seen also in explicit example. So in all Feynman diagrams, there is an overall delta function, momentum conserving delta function that is there. Okay. So 2 pi to the 4 delta 4 P1 to Pn in an n point amplitude. But disconnected diagrams have something more. Okay. Because in disconnected diagram, okay, there is separate momentum conservation in individual connected parts. Okay. So for example, in this diagram, okay, because of this propagator, right, there is also already a delta 4 P1 plus P2. And because you also have the overall momentum conservation, you know from this part of the diagram, there is a delta 4 of P3 plus P4. Okay. So diagram B, for example, okay, and also diagram C, will have delta 4 P1 plus P2 times delta 4 P3 plus P4. Okay. Which basically means that this gives you additional constraints among momenta, okay, than what is implied by overall momentum conservation. Okay. Diagram A has only delta 4 P1 plus P2 plus P3 plus P4, whereas diagram B has delta 4 P1 plus P2 times delta 4 P3 plus P4. So for this, we say that for generic external momenta that satisfies overall momentum conservation, only the connected diagrams contribute. Okay. That if you take say P1 plus P1, P2, P3 arbitrarily, okay, and choose P4 to be minus P1 minus P2 minus P3, okay, which is required by this overall delta function, okay, then diagram A will contribute, okay, but diagram B and C will not. Because diagram B and C, will, in order that they contribute, you need additional constraint. Okay, so you have to go to a subspace of this generic space that is spanned by three momenta to have non-zero contribution from diagram B and C. Okay. And so for this reason, for most purposes, although not for every purpose, okay, we will be dealing with only connected diagrams. Okay, particularly in the scattering amplitudes, right? Suppose you take two particle going to two particle scattering amplitude. Okay. They are the connected diagrams are the ones that are relevant. Is this clear? Any question or comment?
So these external momenta do not have physical significance so far.
Not so far, yes.
Then why are we only considering those cases where only the external momenta add up to zero and not in the...
See, this is necessary because of this is always a part of the diagram, right?
Yeah, yeah.
Okay, so this forces the total momentum adding up to zero.
Yeah.
Okay, so if this is not true, then every diagram will vanish, right? But
Yeah.
I'm saying that after you have use that constraint, right, then these require additional constraint on the momentum for them not to vanish.
Yeah, but like we should consider these, right? Because we don't yet know physically whether it will yield something or not.
Yeah, I agree. We should consider this in general, right? But this is the distinction between connected and disconnected diagrams you should keep in mind. Okay? Because we will see later, I'm not saying that you are throwing away immediately. Okay, I'm just saying that this is a feature you should keep in mind, because later on we will see that when you consider scattering amplitude, okay, then a generic experiment, okay, will not see the effects of these. Okay, because in a scattering amplitude, these will play the role of actual momentum of particles that are coming in and going out. Okay, and there, if for example, if you fix two external momenta and two final momentum, right, for generic values, right, the total momentum conservation, of course, will be satisfied, but the individual momentum conservation will not be satisfied.
All right.
Okay, but at this stage, I'm not saying that we are going to throw this away. Right? I'm just making a distinction between the connected and disconnected diagrams. The disconnected diagrams have additional momentum conservation rule compared to what we have for connected diagrams.
Yeah.
Any other question? So I think I have to stop here, and this is the end of the lecture. So I didn't give too many examples, okay, but I think you have already seen several examples, and you should work out examples yourself. Okay, draw Feynman diagram labeled by momenta, and try to write down their expressions. Okay, including all the integrals and combinatorial factors and everything together.
Hello, sir.
Yes, go ahead, please.
I was saying, when we are writing a theory, we have two parameters. Let's say, in the case of this, in the case of the theory that we are writing, Pifo theory, we have lambda and mass as
Yes.
two parameters. So we should be. Are we supposed to take any values for these two parameters initially? I mean, are they related to the observable mass in any way?
Well, the point is that the relationship between these and observable masses has infinities, right?
Yeah.
Because of this fact that if you think of the physical mass, let's take the observable mass is say A1, right? A1 expressed as a function of lambda and m actually is infinite.
But
So,
like this infinity comes because we are taking higher order terms in the perturbation.
yes,
If we had taken only the let's say the first two orders in which there's no loop momentum integration,
yes,
then we are supposed to get some finite answers.
yes, you will. So there the m will turn out to be the mass of the particle. In fact, that's the lowest order in perturbation theory. You know that m is the mass of the particle, right?
But in exact calculation, they may not be related. You're saying that?
Well, they will be related. They'll be related, but there'll be infinities in that relation. So for any finite lambda, okay, A1 is indeed a function of m and lambda, right? So it will start as A1. Suppose A1 is the physical mass of the particle, right? So the way the relation will start is A1 will be m plus lambda times some function of m and capital lambda, and that function is infinite typically. Okay, plus lambda squared times another function, which is also infinite, and so on. I can probably write this. Okay, so the way the relation will, suppose A1 is a physical mass, right? Let's call it MP. Okay, this is A1C, right? So it will start as M. We know the leading order term is to leading order, right? M is the mass of the particle, right? At the zeroth order in expansion. Then there'll be lambda times some function. Let's call it F1. Well, I have your, let me call it F tilde 1 of M and capital lambda. This function is not necessarily finite. Okay? Then there'll be lambda squared times F2 tilde of M lambda and so on. Okay, so this is the way the expansion will go. So if you are working to lowest order in lambda, right, then M is equal to MP. At the first order lambda, right, when you try to write M in terms of MP, it will also involve lambda, and that is typically infinite, that relationship.
Okay, yeah.
So you're saying we have to find this A1 through some experiment, right?
we have to find the relationship between MP and other physical quantities by experiment. M you cannot find by experiment, right?
MP, I mean.
MP, yes.
This we cannot find by experiment.
MP.
Yeah, I'm asking.
Yes, MP is the physical mass of a particle, right?
So
So all
that should be
observables you can
observable.
find by experiment.
Yeah. So, but now in our renormalized description, some new quantity that I have to observe will have to be in terms of this physical mass.
Yes.
But isn't that a problem? Because, I mean, concerning the accuracy of predictions, like our observation itself depends upon a constraint put on observations.
Well, that's what a theory is supposed to do, right? Theory is supposed to relate two different multiple observations together, right?
Yeah, but in a sort of independent fashion. I mean, like, aren't we sort of going circular in this prescription?
No. Why are you going circular? Because we are giving two parameters, right? So theory doesn't know what the parameters are, right? Theory tells you how to calculate things for arbitrary values of the parameters, right?
Yeah.
Unfortunately, perturbation theory only tells you how to calculate it in a perturbation expansion. Okay? Nevertheless, let's forget about that restriction, right? So theory tells you that how to calculate everything for arbitrary values of parameters, right? So parameters in this case are two observables, say A1 and A2.
Yeah.
So theory tells you if A1 and A2 is this and this, then A3 will be this. Gives a functional relationship. Now we experimentally measure what A1 and A2 are. Okay? That theory is not giving you. But what theory is telling you is that once you know experimentally what A1 and A2 are, then A3, A4, A5, etc. all can be calculated, but is predicted by theory, and that you can now check with experiment. Right?
Yeah, but the problem is that when we are writing something like, well, Klein-Gordon theory is somewhat abstract in the sense that that M could have been anything. But
Yes.
once we have observed it to be MP, we denote it as the physical mass, right?
Yes.
The M
But
in
that's
this
also being
starting
used for
theory
a
also.
parameter. See, Klein-Gordon theory, right? To do this, to carry out the renormalization, right? You don't need to know the value of MP. Right?
Sure.
MP will be a parameter of the theory. Instead of saying that M is a parameter, you now think of MP as a parameter of the theory. Say MP and lambda P. Lambda P is the 4-point coupling that you measure by experiment. So MP and lambda P you take as a parameter of the theory. Those are your A1 and A2. Klein-Gordon theory doesn't tell you what those result values are. But what Klein-Gordon theory tells you is that how to express every other observable in terms of MP and lambda P.
I mean, Klein-Gordon theory, we have with this perturbation, we have has entered with this parameter lambda, which we denote as the coupling strength.
Yes.
And coupling strength, we also say, we will say that nature has fixed it, or like we have fixed it in doing the experiment.
Yes, that is lambda P.
Yeah, and at the end, what should we say the coupling is? Lambda P, right?
Yes, indeed.
And every other thing we'll calculate with using this lambda P instead of lambda.
Yes, true. But why does it bother you?
I mean, we started off by saying that the coupling is lambda, not lambda P.
Yeah, true. But now you call it lambda, to say the coupling is lambda P. Right? I mean, you can change your mind on the way, right? I mean, the point is it doesn't increase the number of parameters, right? It's just saying that M and lambda are not good things to work with.
Yeah, but I mean, it's fine as a theory, but it's okay.
I mean, the point is that imagine that the theory is actually part of a finite theory, like string theory, right? But you can still do this, right? You can always decide which, I mean, instead of saying that M and lambda are your parameters, right? You can still decide that I'll use some other combinations of M and lambda as my parameter, right? I can choose M plus lambda and M minus lambda as my parameter, right?
Yeah.
So what is wrong in doing that?
I mean, I mean, it's fine as a theory. That's what I'm saying. But
Well, it's fine. I mean, as a theory means it's fine as far as you want to make connection with the experiment, right?
yeah,
Then it tells you how to calculate. I mean, whatever you could, if there is no ultraviolet divergence, right? Whatever you could do there, you can do here. So the only thing you cannot do is the theory itself had fixed m and lambda for some reason. Then MP and lambda will also be calculable in principle, right? That you cannot do here because theory doesn't actually fix m and lambda. Quantum field theory doesn't fix, right? In string theory, m and lambda would have been fixed. But in quantum field theory, has m and lambda as arbitrary parameter that you can vary. And because
why,
you can vary m and lambda, you might as well vary MP and lambda p, which are observable quantities.
why do you say in string theory we have ML lambda as fixed? I
Well,
mean,
string theory, the point is you more or less everything is fixed to begin with. Okay, the masses of particles, the unperturbed masses of particles are fixed, and then the perturbation theory, whatever is a shift, right? The difference between MP and M. Okay, because everything is finite, okay, it makes sense there to ask what MP would have been, or the analog of MP would have been.
so by a similar logic, if we are observing the mass of the particle itself, should we also say that speed of light is a parameter of the theory?
Well, speed of light, I mean, the point is there are distinctions between speed of light is used to set the units.
Yeah, I mean, that is also true.
So, I mean, once you have set the units, right? I mean, C h bar, and one normally uses the Planck mass as the other unit, right? But you can use anything else, okay, as the unit. Then all the ratios are dimensionless parameters, right? Those are the genuine parameters. Okay? So in that case, in the Klein-Gordon theory, you can say that because Klein-Gordon theory doesn't know about the Planck mass, right? There you can say that m can never be fixed because m is just setting the scale of the theory. But lambda certainly is a dimensionless parameter there, okay, and the coupling strength, right? So that's a genuine parameter which you can, which is not like the speed of light.
Yeah.
Any other question? Okay, so if there is no other question, I'll stop here and then we'll continue tomorrow. Next week there will be no class, so we'll continue after this.
So regarding the exam,
Yes.
is it fine to submit it in a typed out document?
Yeah, you can submit it any way you want. You can even submit it in type plus handwritten if that is more convenient, right? You can send 2 files because figures, if you don't want to draw, right? As long as you send everything, it can be more than one file.
All right.
Okay. Any other question? Okay. So then the exam will be on Saturday night. Okay, Saturday night to Sunday night. Okay, I'll send out a message again, and we'll resume the class the week after this. Okay, so I'm stopping the meeting now.